Hey everyone. Good afternoon, good evening, good morning, wherever you are. We are ready to start today's 101 about thermal bridges. It's going to be presented by Ed May, a good friend and colleague from New York. And just to give you a brief intro on Ed, he's a licensed architect and a lead green associate. He received a Bachelor's of Fine Arts from the University of Massachusetts at Amherst in 2001. And has a Master's of Architecture from Parsons, the New School in New York City, from 2009. Ed has been an adjunct professor at Parsons, the New School University, as well as an industry professor at Stevens Institute of Technology in Hoboken, New Jersey, where he directed the 2015 Solar Decathlon program. In addition, Ed teaches with the Passive House Academy, the North American Passive House Network, and Passive House Canada. And he's certified by Passive House Institute in Germany, and also by the Passive House Institute in the US, VS, as a certified Passive House consultant. So, it is someone that has a lot of knowledge. He's ready to try to break it down for us in bits and pieces we could, digest and get us going. So with that, I'll cede the floor to Ed.
Well, thank you, Jose. And thanks, everybody, for being here. Thanks to Zach and Kim and Michael, the whole Passive House Accelerator team. These sessions are always fantastic, and it's really great to be here with you guys. So I'm going to try and share my screen, and then we can jump right into the meat of today's session. So can everybody see that okay? You guys can all see my screen? Yes, I'm seeing some nods. All right, fantastic. So as Jose said, my name is Ed May. I'm a reformed builder and architect nowadays, a Passive House consultant and educator. My firm bldgtyp with my partner, John Mitchell, we operate in the New York City metro area, and we have our fingers in sort of all things Passive House. But we come from an architectural background, so our specialty, if we have one, is mostly on the envelope side of the coin, and that often means thermal bridging analysis. So that's what we're going to talk about today, and we're going to dive in and have a chance to kind of talk through some of the important items around thermal bridge analysis when it comes to Passive House buildings. Let's see. So thermal bridging. That's a weird term. It's a weird word. If you haven't heard that word before, don't be alarmed or confused or worried. We're going to talk about what that is and sort of what it means. It's definitely a peculiar term. So we'll define what that is and sort of talk about why it is important and sort of who's asking us to look at these thermal bridges in our buildings. We will talk a little bit here today about where we can find thermal bridges in our buildings. So we'll sort of walk through how we identify and find these thermal bridges when we're doing our design phase analysis of our projects, or we're in the detailing phase of our buildings. And then we'll try and talk about why these thermal bridges are important. So what is it about thermal bridges that are relevant to designing low energy, durable, healthy buildings? Why are we going to put all this time and effort into identifying, managing, simulating, detailing all of these elements? What is it that we care about when it comes to thermal bridges? And then we'll finish up by talking a little bit about how we manage these thermal bridges in practice. And as Jose and Zach said, we'll try and leave some time at the end for questions. So if you do have questions as we get into it, please feel free to add those to the chat, and I'll be happy to take those as we get in. So that's kind of our agenda for today. Hopefully that sounds good. This is obviously a 101 session, so we'll keep it a little high. We're not going to do any math together. Don't worry. We're not going to be doing any simulations, but we want to talk about the important bits and pieces, mostly talk about why it is that we're focusing on these thermal bridges and how we evaluate them for their impacts on our buildings. So let's just start by talking about what is the thermal bridge. Again, that's a weird term. It's a weird kind of, you may not have heard that term before. We use the term thermal bridge. Sometimes you might hear it called a cold bridge in certain contexts as well. A thermal bypass is also sometimes used in certain circles. But it basically denotes or refers to any place in our building where we have a disruption or a change in the let's call it the standard assembly. Any place where we have a break, a discontinuity, a disruption in our insulation in our building. They come in all sorts of different flavors, and they can happen for all sorts of different reasons, but we label all of them as thermal bridges. In the case here, we're sort of categorizing our thermal bridges into two different buckets, or two different flavors, if you will. And this really has to do with the way that we assess and account for the thermal bridges in our modeling procedures. We have a bunch of thermal bridges, which we might call repeating thermal bridges. So these are elements like rain screen facade clips, like you see in the left there, that occur at some regular interval or regular spacing across the assembly, across our building. Those are going to get baked into or built into the basic U values of our assemblies. So that's the way we're going to kind of take those into account. There's another type of thermal bridge, which you see on the right-hand side there, which goes by a bunch of different terms, but maybe in this case, we could call them the non-repeating thermal bridges. These are discrete sites of disruption in the building envelope. In this case, we're looking at those concrete balconies that penetrate through the insulation layer of the wall. Those occur for some distance across the facade of the building. So we have a couple different cases here. For today's session, we're mostly going to focus on those non-repeating, or sometimes we might call them construction thermal bridges. That might be one of the other terms that you would hear people use to refer to those types of unique disruptions. These are conditions or details that are not built into the basic U values or R values of your basic assemblies there. And so we need to account for the heat loss of those details in a slightly different way. So we'll kind of talk about that as we go in. So that's mostly what we're going to focus on in today's session here. Now, again, why do we care about these thermal bridges, or sort of what is, from a high level, one of the reasons that we're tasked with looking at these thermal bridges? Well, we'll talk about the building physics implications in a little bit, but from a regulatory perspective, there's two main reasons why we would be focused on these thermal bridges. The first, and the one that we've seen for the past several decades has been the Passive House standards and frameworks, whether PHI or FIAS, both require that we account for these thermal bridges, whether repeating or non-repeating, in our Passive House models. So the various Passive House certifications, whether we're talking about new construction or retrofits, PHI, FIAS, whatever flavor of Passive House you're doing, they're all going to require that we take into these thermal bridges into account, and that we keep a very careful watch on these thermal bridges. The other is relatively new. We're starting to see some building codes, notably where I work in the New York City area. The New York City Energy Code is now requiring that we account for, or at least note and recognize, all of the thermal, or not all of, but some of the key thermal bridges on our buildings moving forward. I would anticipate, much like airtightness over the last few decades has sort of worked its way through the various building codes around the country, I would anticipate that these types of requirements around identifying and then mitigating thermal bridges are going to start working their way through various energy codes. And of course, in America, these things will work at different speeds. So some places will adopt these types of requirements relatively quickly. Others will lag behind by a few years, just like airtightness, I would say. So you keep an eye out for those. This requirement around identifying and managing thermal bridges is starting to pop up in certain building codes, and I would definitely anticipate that we'll see more of that in the future. So, okay, so we're going to focus on these thermal bridges. So what are common thermal bridges, and how do we find them? How are we going to identify these thermal bridges if it's during our design phase? Well, we'll go through a couple of kind of rules, some rules of thumb, but some kind of basic tests that you can do of your details and your assemblies as you're working through the design, as a way of identifying the thermal bridges. We'll come back and talk about how we assess the impacts and the importance of thermal bridges. But for the most part, what you're going to be looking for are sites where you have a break, a discontinuity in the insulation layers of your building. I think this is often best done, what's the word? not in the computer. Print out a section, a detail, and color it in. I'm a big fan of using color. Use yellow for the insulation, use red for your air tightness. If you ever find a spot where there's a big gap in your yellow insulation, that's a real easy visual cue that you have a thermal bridge at that site. You don't need any sophisticated analysis software. You don't need to do any simulations. You really don't need anything more than your eyes and a colored pencil or a highlighter in order to find those types of discontinuities. So you're going to be looking for those types of gaps in the insulation layer. Those are going to be a visual indication of a thermal bridge. So anywhere that we have a break, a space, a gap, a failure to continue the insulation around the entire building, those are going to be considered thermal bridges. Now we'll come back and talk about how we would then go in and assess the magnitude of the thermal bridge, but you're going to flag these and say, listen, these are all thermal bridges. The rule of thumb that we would typically use is that if you have less than, let's say, an R10, if you're working in US units, an R10 insulation, then that would be considered a thermal bridge. So sort of keep that one, again, just a rule of thumb, but you look for areas where the insulation has thinned up or been reduced below that R10 threshold. And if that's the case, you're almost certainly going to have some sort of thermal bridge that you need to then assess. So you're going to be looking carefully through your assemblies for these types of details. One other place where you're going to have thermal bridges in almost all cases is going to be at your windows. So the site where your big, fat, well-insulated passive house wall touches your narrow, thin, delicate little passive house window, those are almost always going to be sites of additional heat loss, additional thermal bridging. So those, we call them, it's a special type of thermal bridge known as a window install. So your window install thermal bridges are going to be taken into account in your building as well. These are going to be unavoidable. You're going to have to model these or at least manage these and make sure that they're built in to your energy model. These can oftentimes be quite significant. So you're going to have to work hard to try and minimize these if you're seeking to achieve one of those passive house standards. One of the easy things to look for when it comes to window thermal bridges has to do with the alignment of the window in the insulation layer. So what you're going to look for is you're going to look for your insulation, you're going to look for your window, and if those two things are out of alignment, if they're not connected or continuous with one another, which is often the case, that's going to be an indication of significant thermal bridging. So here you can see we've got significant misalignment. So the window is way to the outside of this building, and then the insulation is sort of more to the inside there. And then in addition, we have all sorts of metal elements like the ledger angle there and a bunch of flashing and other trim elements there, which are all causing or adding to the heat loss around the perimeter of the window there. So the windows are going to be an important site to assess in all passive house buildings. These are going to be one of the key areas of thermal bridging, not only because of this misalignment, but also because of all the other stuff that happens at those window installs, all the flashing, all the trim, all the other kind of weird bits and pieces there. So these have to be very carefully detailed to minimize and reduce the amount of thermal bridging. And then the last area that you're going to look for are places where we have changes in direction. So any place where the insulation changes direction more than maybe 30 degrees or so, these are going to be sites of additional thermal bridging. That we have, these are what are known as geometric thermal bridges. And in practice, these sites of change in direction are often accompanied by additional construction thermal bridges because you often have additional stuff at those corners, additional studs or blocking or fastening or trim or something else that's going to happen at those corners as well where your building envelope changes direction. So these are all areas that you're going to look for during the design phase, and you're going to flag these different areas for further analysis, right? So this is sort of step one. We're going to go through our design and we're going to try and identify all of these various thermal bridges. There's one other test that we might do. You might say, well, am I working on a building which is about thermal bridges, is somehow designed to increase the amount of thermal bridging? In that case, you do a really simple test. If you're looking at the building, then the answer is yes, you're looking at a thermal bridge. If the answer is no, then you're looking at the sky, and in that case, you don't have to worry. Although I guess maybe it brings up the question, if you have a thermal bridge on a building which is entirely thermal bridges, is it still a thermal bridge? We can get into that discussion later. I kid, because it's such a terrible building. So what? So who cares? Okay, so we have these thermal bridges. But why do they matter? Why are the building codes asking us to look carefully at these things? Why are the passive house standards requiring that we dive in and model these things? Why are we going to spend so much time and effort on these issues? Fair warning, we're going to have some new vocabulary on the next slide. If you need to leave, I understand. It's okay. It's a Wednesday. Maybe it's not the right time for learning new words, but we're going to learn just a few new vocabulary words that we need to understand before we can kind of wrap our heads around these thermal bridges. So how are we going to evaluate our thermal bridges? Well, the first thing we're going to do, the first reason we're going to watch for these thermal bridges is that each of these thermal bridges is a site of additional heat loss. So one of the reasons we care about thermal bridges is because these are sites of extra heat loss through the envelope of our building. And here's the new vocabulary terms that we need to be familiar with. Whoops. Oh, there we go. So the way that we're going to quantify these thermal bridges is through the use of the psi value, or you might sometimes hear it pronounced C value. It's a Greek letter, C or psi, however you prefer. That is a measurement of the heat loss per foot of detail. So this is one way that we're going to assess and quantify the heat loss of our thermal bridges. The other might be the chi value, another Greek letter. We use that to denote the total heat loss for a thermal bridge. You might use that if you're trying to assess the heat loss for a beam or a column, some discrete element that penetrates the insulation layer. So the psi value or C value, that's going to be used to represent or account for heat loss across a linear thermal bridge. So for instance, in the balcony shown here, we might have an additional amount of heat loss that occurs for each foot of balcony. And then the chi value there is going to be used to account for heat loss through discrete sites of penetration. So beams, columns, that sort of thing. So two new vocabulary terms. We're going to use those throughout the rest of the presentation there. So don't be alarmed. I know it's weird, Greek letters and all that kind of stuff. But these are just the ways that we account for and label the heat flow impacts of our thermal bridges. So psi value and chi value. Now, the other reason, so there's two reasons that we care about thermal bridges. The other reason that we care about thermal bridges is that thermal bridges, because of that excess heat flow, because of that extra heat loss, are sites of low temperature. And low temperatures lead to condensation in certain circumstances. So we're worried about condensation risk. This goes directly to the durability and the health of our buildings. The way that we design out mold and moisture issues in our buildings is by designing out thermal bridges. Now, how are we going to account for? How do we evaluate the condensation risk of our thermal bridges? For that, this is the only other new vocabulary term that we have here today. We're going to use the temperature factor. So the temperature factor, that's what we're going to, that's the measurement that we're going to use to evaluate the condensation risk. And we'll take a look at how these work in a little bit of detail in the next little bit. But we just want to kind of tee these up here and label these things. I would note that in a lot of reference documentation, you'll often see the temperature factor referred to as the FRSI, or sometimes you might also see it known as the FRSI equals 0.25. There's a bunch of different ways that people kind of refer to this, but they're all referring to the same thing. So we have this number, this temperature factor, and that's what we use to evaluate condensation risk. And again, I'll come back and talk about how we calculate it and what it means and all that kind of stuff. So, okay, so we have these values, and this is what we're going to use to evaluate our thermal bridges. We look at the heat loss and we look at the condensation risk. Well, where do these numbers come from? How do how do I get these numbers for my detail? There's a couple different ways. First, you might go to a existing catalog of details. You might say, well, I'll go to one of the ISO documents, 14683. I might go to a thermal bridging catalog like the BC Hydro Thermal Bridging Guide. You might go to the PHI Thermal Bridge Catalog. You might go to a Berkhauser book, or you might go to, there's all sorts of publications that have assemblies and details where someone has calculated the psi values and chi values for all sorts of different details. So you might just go look for your detail in a catalog or a compendium someplace, and then use those published values. That, in my experience, has never been super useful. For the most part, what we find with our projects is that we often have details that don't match the ones in catalogs. I'm not a huge fan of these types of catalogs. I just don't think they ever really capture all the different flavors. And certainly in the retrofit work that we do, those are almost never in these types of catalogs. So the second way that we might find or create the psi values and the temperature factors for evaluation would be to just do the work ourselves. This is going to be by far the most typical method for figuring out what the psi values are, chi values are, what the temperature factors are. You're going to use a specialist simulation tool like Flixo or Dartwin's mold program. Those would be two good examples of specialist simulation tools that you might install on your own computer and then use to calculate your own psi values, your own temperature factors. These tools are fantastic. There are many of them on the market these days. If you want a recommendation from me for the tools, certainly the ones that we use in our office are InfoMind's Flixo tool, and then Dartwin's, that one for two-dimensional details, and then Dartwin's mold tool, that one for three-dimensional details. And we'll show a couple examples of sort of how those work. But this work is relatively straightforward. The tools are actually not that difficult once you kind of learn them. There's a learning curve, of course, but they are fantastic tools to invest in. They're not too expensive, and they're well worth having if you do this kind of work regularly. One note on that front, just to sort of talk about, if you are going to be doing this type of work, in addition to the simulation tools themselves, so in addition to sort of owning the simulation programs, you should also have a library of the rules documents. So there's a couple of important rules documents, just PDFs of 8.5 by 11 or A4 rules that you should have in your sort of personal library. And these you will refer to and reference as you're building these thermal bridge simulations. We've sort of flagged a couple of them here. The most important ones are the ISO 10211 and then the ISO 13370. Those would probably be the most relevant. And if you're doing Windows, it would be the ISO 10077-2. So those would be important. Those numbers just refer to, that's just the number of the document. And so you'd want to own those or have those in your library as well so that you can refer back to them. So these are just a list of procedures and rules on how to do these simulations. Well, lastly, one other thing just to note before we'll look at a couple examples here of heat loss and condensation in some details. Just one last thing when it comes to evaluating, it's worth highlighting, and I'll say this several times, not all thermal bridges are created equal. So just because something is a thermal bridge does not automatically mean that it's a problem for your building, either on the heat loss side or the condensation side. Both a wood stud and a steel stud are thermal bridges. They are sites of discontinuity of the insulation layer. They are disruptions or bridges from the inside to the outside through the insulation. But they are not equally impactful on the building's heat loss or condensation risk. The steel stud is going to be much more impactful, is going to be much worse for the building when it comes to overall energy performance and condensation risk than the wood stud. So they are both thermal bridges, but the wood stud is nowhere near as bad as the steel stud. So just something to keep in mind. While they are all thermal bridges, that does not automatically mean that it's a catastrophic fail for your building and you have some sort of horrible problem. You really need to look at the detail carefully and assess the magnitude of the impact. How much heat loss are we talking about? And then what type of condensation risk do we have? So just kind of keep that in the back of your mind as we look at a few examples here. So let's take a look at a couple of different actual details. We'll talk about heat loss, how we evaluate for heat loss, and then we'll look at condensation as well. So here's a very typical detail. This is a parapet detail, commercial style construction. You've got a concrete roof deck with a concrete parapet. You've got a well-insulated wall, and then you've got a nicely high insulated triple glazed window. But in the detail on the left there, we have a pretty significant thermal bridge where the parapet disrupts the continuity of insulation. Right? So we have the wall insulation and the roof insulation, and they don't ever touch each other. They are not continuous because of that thermal bridge. There's a couple different ways that we might go about addressing a thermal bridge like this. Maybe one good solution would be to just take that insulation up and over the parapet and around such that it connects back to the roof insulation. Right? So that would be one typical detail that we might see in practice. Another option might be to use some sort of a thermal isolator, some sort of thermal break at the base of the parapet. There are several products that would be suitable for that. So that might be one other solution. No matter which solution we choose, though, we want to evaluate these thermal bridges for both their condensation risk and their heat loss. So again, let's take a look at heat loss first of all. So the first step in evaluating these details for heat loss would be to calculate the psi values. Remember our new vocabulary word there. The psi value is a way that we account for or measure the heat loss of a linear thermal bridge, a detail like this that exists for some distance across the facade of the building there. You can see on the bottom that we've calculated 3 different psi values using one of those specialist thermal bridge simulation tools for the 3 different details here. And you can see the relative magnitude of the psi values. Now, the psi values themselves have really stupid numbers. So 0.154 and 0.089. These are not very human scale numbers. Very difficult to kind of assess which one is better than the other and how much better is 0.025 versus 0.154, right? These are just not very, intuitive numbers for human beings. So what we really need to do is we need to take these psi values. So this is the heat loss for 1 foot of detail. We need to take these psi values and we need to play them out in the building, in its climate, to see what the total impact is of those different details. Now, the building that this detail happens to come from is a reasonably large building. It's 400 units or so in New York City climate. It's about, I think when we counted it up, is about 2,000 feet of parapet. So you've got about 2,000 linear feet of this detail, if you count up all the way around the roof of the building there. And it's in New York City, so kind of a mixed climate, not a super severe climate, but certainly reasonably cool in the wintertime. So a reasonable amount of heat loss. And you can see in the way that we've done the math there in the 3 blocks, on the left-hand side there, if we were to leave the detail uninsulated, if we were to leave that thermal bridge in place with no mitigation efforts, you might see something like an extra 37,000 kV2 per year of heat loss, or if you prefer normal units, maybe another 11,000 kilowatt hours, right, per year. So that's the extra heat loss of that thermal bridge. If we do something like take the insulation up and over and around, remember that reduced the psi value, and you can see as a result here that might drop our total additional heat loss to maybe 6,000 kilowatt hours per year. So this is additional extra heat loss above and beyond the heat loss of the wall and the roof. This is extra heat loss. If we use the thermally isolated detail, the one on the far right there, we could maybe reduce that extra heat loss down to maybe 1.7 or 1,700 kilowatt hours per year, right? So in all cases, we have some additional heat loss that results, but obviously that thermally isolated one is going to be much, much better than the uninsulated one on the far left there. And really what you need to do is then take this information and build this into your energy model, right? So you look at these and you say, is it good? Is that good? Is it bad? Is 1,700 kilowatt hours high, or is that low? Is that too much? Is it, where does that stand relative to the overall building? And that's where the passive house frameworks really come into play, right? The passive house frameworks say you should achieve X level of heating energy demand and cooling energy demand. So you have this energy budget And these thermal bridges impact or spend down that heat loss or energy budget. And so you really need to then take this information and embed it or put it into the whole building energy model to see what the impact is. So that detail we were just looking at there, let's say that we did the thermally isolated or thermally broken option. So it was about 1,700 kilowatt hours per year, or I think, what was it, about 6,000 kBTU per year, something like that. This building in total, when you add in all the parapets and all the corners and all the balconies and all the footings and all the slab edges and all the other thermal bridges, has something like an additional 250,000 kBTU per year of heat loss. But it's a very large building. And so while that's a large number, it actually only represents something like 8% additional heat loss. So what does that mean in context? Well, it means that if we count up the heat loss through all the roofs, floors, windows, we would add an additional 8% to represent the thermal bridges of the building there. So that might be high, it might be moderate. It depends on your building, what your goals for the building are. In this case, perfectly fine. The building here is meeting all of its FIAS heating demand targets, cooling demand targets, total energy performance targets. So the impact of those thermal bridges is minor, is not nothing, but is minor compared to, as you see in the graphic here, something like the window spec or in particular, the ventilation equipment for a big building like this. That's going to be much more important than the thermal bridges. So plus 8% heat loss, that might be that's a good kind of moderate value. Another example, just to give one more data point, this is a retrofit building. This one, a EnerFit retrofit to the PHI standard. This one, very different assembly, right? Very, very different types of construction, very different materials, very different application. This one has around 4% additional heat loss from thermal bridges. So just a couple of data points there to kind of give you some anchor. Something like 4 to 10% would be a reasonable number for additional heat loss due to thermal bridges. When we're in the early schematic design phase of projects, before we even know what the building is built of, we would typically use something like 10 or 15% as an allocation for thermal bridge heat loss. So that's not unusual at all. We would sort of build that into the energy model in the earliest phases and then spend that down on actual details as we get into the detailing and construction drawing phase. All right, so our thermal bridges have an impact on our heat loss. So that's one of the reasons why we want to assess our thermal bridges. That's great. The other reason we assess thermal bridges has to do with condensation. So the other area, the other way that we're going to evaluate thermal bridges is for their increased condensation risk. And again, the way that we evaluate, the value that we calculate and look at when it comes to condensation risk is this temperature factor. So the way this works is we're going to calculate a temperature factor for our detail. And then we're going to say, is that temperature factor above the threshold or below the threshold? If it's above the threshold, we can consider the details safe from condensation. If it's below the threshold, we would consider that risky or at risk of condensation. Well, okay, so A, how do I calculate the temperature factor? And B, where does the threshold come from? What is this threshold? The temperature factor threshold is one of the other places where the Passive House frameworks are incredibly useful. So whether you're working in PHI or PHI US, depending on your building, your climate, and your relative humidity, you will have a target threshold value for your temperature factor. So this is built into both the PHPP, as you see on the left, and then FIAS has an online calculator where you can see the critical temperature factor, in this case for Windows. So FIAS has a slightly different way of doing it, but they both look at the temperature factor and say there's a minimum threshold, and you cannot go below that threshold without being at risk of condensation. All right, so we have the threshold. So the threshold is climate specific and project specific. I'm going to get it from my Passive House tools. So I have this threshold number. So how do I now calculate the temperature factor for my detail? We're going to use the same simulation tool to simulate the overall performance of the detail. We're going to determine what the minimum interior temperature is, and that minimum interior temperature is used to calculate the temperature factor. So let's look at an example here. So we've got three window details. On the left, same detail. The only thing that we've changed here is the flashing, the sill pan. So this is a window sill detail. On the left, you can see a window sill with an upturn, kind of a more old-fashioned metallic sill pan with a back stand there. In the middle, we have a continuous metal sill pan, but with no upturn. So it doesn't actually go from inside to outside. It's sort of embedded in the construction. And then on the far right, we have a non-metallic sill pan. So a rubberized flashing sill pan, a more modern construction method. So we have three different simulations here. So we execute using our simulation tool. We execute the simulation for all three of them. Part of what the simulation tells us, in addition to psi value and heat flow, is what those interior surface temperatures are or predicted to be. So you can see here that we have three different interior minimum surface temperatures based on the configuration of the metal flashing. So on the left there, we can see we have a minimum surface temperature of 37 degrees Fahrenheit, in the middle, 48 degrees Fahrenheit, and on the far right there, 55 degrees Fahrenheit. So this is all information that we gain from these digital simulations, again, whether you're using Flixo or Dartwin or what have you. We take that minimum temperature and we input it into this very simple equation. I know, I said we wouldn't do any math, but this is just subtraction. This doesn't count. So you're just going to plug the minimum temperature value into that very simple equation, and that's going to yield your temperature factor. And so you can see here that we get a temperature factor for the detail on the left of 0.4, a temperature factor for the detail in the middle of 0.61 or 62, and then a temperature factor for the detail on the far right of 0.73. And the way that we evaluate these is we take those temperature factors and we compare them to our project-specific threshold. Go back one slide. Remember, we have our project-specific threshold. So let's say that we're using the PHPP on the left there. We would have a minimum FRSI of 0.65 according to the PHPP calculator. So we take 0.65 and we compare that to the modeled temperature factor. So is 0.402 above or below 0.65? Well, it's below. So therefore, that would indicate that that detail is at risk of condensation. So you move to the middle detail. Is 0.62 above or below 0.65? Oh, it's below. So that would indicate that that middle detail is still at risk for condensation. It's a little closer to the threshold, but still probably at risk. So you'd move all the way to the right-hand side. Is 0.739 above or below 0.65? Well, it's above. So that would indicate that that detail is safe from condensation risk. So that's how we would actually use those tools and that temperature factor in practice to evaluate different details to see whether or not they're meeting our passive house goals for durability, health of the building. Hopefully that makes sense. Let's look at just a few more quick examples, and then we'll talk about managing thermal bridges, and then we'll leave some time for questions, of course. This is a slightly different detail. So this one is a three-dimensional detail. So this would be one where we would calculate a chi value for the heat loss factor, but we would still use the same temperature factor for assessing condensation. So this is a case where we have some steel, which is actually embedded in the wall. Now the steel never goes from inside to outside. It's always covered by wood, but nonetheless, we have steel, which is impinging on and disrupting the insulation. And so this would definitely be a case where you'd want to assess this for interior side surface temperatures and condensation risk to make sure that you didn't have any issues on that steel. So because of the nature of the detail, because it's a three-dimensional connection, I guess they're all three-dimensional connections, but because of the way this geometry works, we need to do this in a 3D thermal bridge. So we need to do a three-dimensional thermal bridge analysis. So we would do this using another specialist tool that we would use to build up the model and then execute a simulation of the model, but it's following the same procedures. What are we looking at? We're going to look at the heat loss and we're going to look at the condensation risk. So here we take our minimum interior surface temperature after we execute the simulation, 52, 53 degrees Fahrenheit or so. We plug that into our simple equation and we get a temperature factor of 0.72. And remember, we take that 0.72 and we compare it to our project specific threshold. Say is it above or below the project specific threshold? In this case, the project specific threshold was 0.7. And that means that this detail is anticipated to be safe from construction. So yes, it represents a small amount of additional heat loss, but it is not at risk of condensation according to the simulation results shown here. Let's show just one other example of a case where we have an opposite, where we arrive at the opposite conclusion. This is another commercial detail. This one, a commercial podium with residential above. You can see the concrete floor slabs there. This one, a FIAS project, and like many commercial podiums, it's going to have some cantilevered steel, which is being used to support an entry canopy, to cover the entryway of the building there. And rightfully, the design team came and they said, well, we know we have to have this cantilevered steel, but it's passive house, so we can't have steel go from the inside to the outside. So we want to use a thermal isolator, right? There are many of these types of products. So we're going to install a thermal isolator in the steel beam here, but we were not sure where to put it. Should we put it in the stud cavity, or should we put it out in the continuous insulation layer on the outside of the stud wall there? So we took this detail and, similar to the last one, build up a three-dimensional model. Because of the nature of this detail, you kind of need to assess it in 3 dimensions. And so you build up a three-dimensional model of the condition here. You can see here the thermal isolator in the stud cavity, so inboard of the air barrier there. And when we executed the analysis here, what we found was that while the thermal isolator does a pretty good job, it's not perfect, but a pretty good job of minimizing heat flow and reducing the chi value of this detail, the heat loss magnitude of the detail, it does result in some relatively low surface temperatures. And the reason that that's a problem in this case is because those cold surfaces are on the inboard side of the air barrier. Right? So we have warm, moist air inside of the space, and it is uninhibited from coming into contact with that cold steel, right? So we have that cold steel coming through, and we have that cold edge along the bottom. And if the warm, moist air from the inside comes in contact with it, we're at a condensation risk. You see very low surface temperatures there. So the fix in this case is relatively simple. We take that thermal isolator and we just move it outboard of the air barrier. So if we just move it 4 inches so that it's on the other side of the sheathing, the other side of the air barrier, out in line with the continuous insulation, you can see that now we have much better surface temperatures on the interior face, and we don't have any risk of condensation. 44 degrees is still low. There were some other mitigation efforts that the team took in order to improve that even a little bit further. But for the most part, a detail like this would be sufficient for avoiding any condensation risk. So that's the way we would actually use these values in practice to influence our details. We're going to look at the heat loss, and we're going to look at the condensation risk, and we're going to use those to evaluate and then hopefully improve our details so that they satisfy those passive house criteria. All right, just real quick, let's talk about managing thermal bridges. And then again, I'll leave some time here for questions for sure. Just from a high level, the only things that we can manage are things that we measure. So one of the very first steps in managing thermal bridges is just to properly account for all the thermal bridges. So even if you don't improve any of your details, thermal bridges, just the act of cataloging, identifying, and tabulating all of the thermal bridges is a useful exercise. And so, yeah, we'll leave it at that, just to say that that is an important part of the process here, is just having a list of all the details and the thermal bridges. Even if you never get to the optimization step, just doing that accounting is really important. There's also something, this is kind of a larger discussion, but we need to execute our details to a certain level of resolution in order to do anything useful. This is kind of a tough pill for a lot of teams to swallow, but there's really nothing that we can do with a detail like this. There's no relevant analysis that can be executed. There's no useful feedback that can be provided. There's no realistic decisions that can be made based on a detail with almost no detail. And so we kind of need to think about how we execute our detailed drawings a little bit differently, so that we can actually generate this kind of useful feedback. In an ideal scenario, this would not wait until the very end when it's almost impossible to make any changes. So there's maybe a necessary revision to some of our practices when it comes to meaningfully integrating thermal bridge analysis into our processes. The other thing I would say, just from, again, kind of a high level, is follow the data. Your assumption, until you've done a few thousand of these thermal bridges, your assumptions and your instincts around what matters are probably going to be wrong. And so, especially in the early days, follow the data. Do lots of simulations, do lots of iterations, work through the options, and then again, follow the data. What data? You're going to be looking at your psi values, you're going to be looking at your chi values, and you're going to be looking at your temperature factors, right? Those are the three things that we use to evaluate whether a thermal bridge is good, bad, or otherwise. And so iterate, 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 follow the data. Just a few very last pieces here. If you want like just a sort of if you want just a quick fix, if you're not interested in doing any of the simulation, you just want to know, well, how do I build a building where I don't have to worry about this? Just use continuous exterior insulation. That's a really good way to just avoid having to worry about much of this stuff in general. You're going to have all sorts of mistakes and errors and failures in your framing. That's just the nature of the business, especially with residential projects. But if you can put a nice continuous layer of insulation around the building on the outside, well, that covers up a multitude of sins and issues. So one of the easiest ways to manage or avoid having to worry too much about thermal bridging is just to use continuous exterior insulation. I know it's more difficult. I know the siding application can be challenging. I know some contractors are very frustrated with it, but it really is a very effective way of managing thermal bridging and just reducing a lot of the headaches around thermal bridging, whether at the residential or the non-residential scale. And just the last 2 points here, we want to use thermal breaks wherever possible. There's many different options for these types of thermal isolator products. Here you can see a specific example of a concrete balcony thermal isolator. This from a project of ours from 10 years ago now. These products are available, and you should be integrating these into your design wherever possible, which leads me to my last point here. It is up to you to learn about the ecosystem of products that are available to help manage your thermal bridges. You do not have to invent these processes or software or products from scratch. There is an entire industry out there who's dedicated to helping you reduce and eliminate thermal bridges on your buildings. It's up to you to tap into that network of products and suppliers and solutions. So educating yourself about those different options is incredibly important. There are some very good sources for this type of information now. And so it's really up to you to kind of tap into and learn about that ecosystem of products. But again, don't think that you have to invent all this from square one. People have been doing this for decades, and there's a lot of great resources and products that you can utilize on your projects. Lastly here, the very last slide, if you're interested in learning any more about this, all of the various Passive House providers, whether we're talking about VIAS, Passive House Network, Passive House Canada, Peel Passive House, all have various thermal bridging courses. So if you want to learn how to use any of the thermal bridge simulation software or really dive in deeper, those are great places to go. And then there's also a new thermal bridging academy through which I think Dylan Martello is teaching from Stephen Winters Associates. I haven't seen that one yet, but I've heard that I've heard good things, and so that might be another one to check out there at the bottom, which is awesome. And so lots of great resources for learning more. Again, you just need to know to tap into those networks that already exist out there. All right, so that was a bit of a whirlwind, but I would be more than happy to take any questions in the last few minutes that we have here together. I know that went a little longer than anticipated, but hopefully that was relevant and useful. And certainly I'm happy to stick around for a little while to answer any questions that y'all might have.
Thanks, Ed. Great presentation. Yeah, we're running a little longer, but that's fine. We'll just pass it along to the sponsors, and Kim, take it away, and I'll just add some notes because I know we're going to have some good questions and maybe a path forward to get them all answered.
Yeah, great. Thanks, Jose and Ed. That was incredible. Thank you so much. I just want to spend a couple moments to thank the fine organizations that make all of our work here at Passive House Accelerator possible. So a big thank you to our stakeholder partner, NYSERDA. I'd also like to thank our founding sponsors, 475 High Performance Building Supply, Baxtangui Architects, Glavel, Minitaire, Partel, Rockwell North America, Stocorp, and Zola Windows. Thanks to our champion sponsors, Bewizo, Gradient, Icon Windows and Doors, Intelligent Membranes, PH Air Seal, Proseco, and Source 2050. And also thank you to our patron sponsors, Brennan, Coltraco Ultrasonics, Euroline Windows, Holstrom System, Inotech Windows and Doors, Lamelux, Longboard, Owens Corning, RDH Building Science, and Sanderson Sustainable Design. So big thank you to our sponsors. I also would like to just to mention to everybody that we've been working hard on this exciting new event called Reimagine Buildings 24. It'll be on March 7th and 8th, and we encourage everybody to register. And I just want to share a really quick video reel about it that kind of gives you a sense of what's in store. So I'm going to show that now, and then we'll get to questions. Imagine you could learn about 24 of the best buildings solving for climate change, instantly become part of a global movement, and gain the knowledge you need to create real change in what you do every day. Join us for a one-of-a-kind, 24-hour, around-the-world, global online happening, Reimagine Buildings 24. We'll circumnavigate the globe, unveiling a new, innovative building project every hour, complete with actionable solution sets, expert insights, and key lessons learned. We'll connect you with peers from around the world and from your region, so you can build the network you need to create buildings that make a difference. We all know that time is of the essence, that climate change is already here, and that today, too many of our buildings are not only making the problem worse, but also leave us vulnerable to climate extremes that are already here. But that's all changing. A global movement is turning it around, reimagining buildings as resilient and healthy havens, as climate solutions. Tradespeople, builders, architects, engineers, developers, policymakers, and just regular people making it happen on the ground on every continent of our beautiful planet. Join that movement at Reimagine Buildings 24. All right, thanks everybody.
All right, thanks, Zach. So we'll be going on till 1:15, right? I think that's our break. Okay. So Ed, I guess I'll just start with some questions. And before I do that, Zach and Kim, do you think would be beneficial if we just grab all the questions that may not be answered during this time, send them to Ed, maybe add them on the comments on the YouTube channel when this is posted? I think there's good information, the questions that we have here. So just kind of putting it out there.
Sounds great.
Okay, so the first question comes from Alec Gardner. Alec, are you on the call? So you could ask your question.
I am. Ed answered most of it. I asked early on and covered it. So, but I guess there was maybe some follow-up could just be, are there, I think I can answer my own question, honestly. Maybe jump to other people's questions since we are time constrained. Thanks.
That's okay. That's okay. Thanks, Alec.
Yeah, no problem. I'll send the question to Ed though, because I think there's a good snippet there that may be interesting to dive into later. So just to go on the next question then, Paul Heron. Is Paul on the call? Maybe he jumped off. So Paul's question is, for the psi value, you say it is a linear value per foot. What direction do you measure that linear value?
That's a good question. Let me see if I'll go back up. Let's see. So let's say for a detail like this, right? Getting a little off in the weeds, but it's okay. You would measure the length across the facade. So imagine you're looking at an elevation of the building, like a flat elevation, like an elevation drawing. You measure across the facade. So this balcony might be, I don't know, what's that, 10 feet long. So the psi value is a measurement of heat loss per linear foot. And maybe you've got 10 feet of balcony. To the other example that we used here, I was showing the parapet. The parapet you would measure around the perimeter of the roof. So it's, again, measure along the facade, if that makes any sense.
Yeah, I think another way to look at it is if you have the plans, just whatever the length that's coming at you from the drawing is is the length of the thermal bridge, right? That's an easier way to look at it if you're
There you go,
just looking at
measuring
drawings.
measuring it in plan. Yes, for a detail like
Yeah.
a parapet, measuring it in plan would be a great way to do it. You're exactly right. Yep.
Yeah.
Good point.
So next up is Harvey Minnick.
Hey, Harvey.
Ed, how are you? Nice to see you again. I'm
You
not going
too.
to ask you anything hard. It's just going to be a layup. But one of my big things, and Zach knows about this, is that I think we need to standardize window install from beginning to end. And I know that's people fight on that, but why don't we just go through my question, which is very quick. Is there a best practice for window installation as well as corners or changes of directions that you could recommend? I know you said earlier on change of directions, if you have a problem, just throw on
talking to
but it's just
American.
something you can
I've
go
got a
forward.
chat line go with these experts in America.
Oh, please.
Sorry,
I am an
muted them.
expert. Thank you for saying that.
Indeed. So best practice for window details. That's kind of the crux of the question. You know the answer to that, Harvey. The answer is it depends. Sadly, as a general rule, you want to get your window in line with your insulation. So in most situations, you want to get your window in line with your insulation. If your insulation is in the middle of the wall, if it's a double stud wall, then that means something different than if it's continuous exterior insulation. You might put it on the outside. There's a whole other level of complexity which goes into the shading question. So depending on where you locate the window, you may have more or less shading, which also changes the overall energy balance. But so it depends. But the typical answer is try and get your window in the middle of the insulation layer, whatever that happens to be on your specific project. But
Yeah,
yes, standardization would be
sure.
amazing. The more standardization is always a good thing.
Well, one of the other issues of change of direction is the fact that we always seem to find that if you have dormers on a passive house build or any kind of build, that's always a difficulty. So that's where I came up with the change of direction, because I think a lot of people, when they're looking at it, is they're looking at passive houses and they're seeing more of a modern look or a very monolithic look. And if you want to have a traditional home, usually you're going to have some types of peaks and you're going to have some types of valleys and you're going to have that dormer look. And so that's why I asked the question about the change of directions. And that's it for me. Thank you so much for answering.
No, good point.
Yeah, thanks, Harvey. That's a good point too. Not all passive houses have to be boxes, and it's our job to adjust to the design and to make sure that the client gets what they would like to have, and that's what we're going to have. It's
if I might just add,
for this.
I'll just add one thing to that, Jose. It's a really good point. The difficulty is that the more changes in direction, the more jigs and jags and ups and downs and dormers and bits and pieces, the more challenging it is from a thermal bridging perspective. So one of the reasons that you see so many boxes is because it's a lot simpler and easier. That doesn't mean it's better. It just means simpler and easier. And so one of the things we have to be able to do as designers is to be able to accommodate those desires. And that means becoming facile with these thermal bridge analysis tools so that you can deliver the design that people actually want and manage all of those issues when they arise.
Oh yeah, definitely. That's part of the fun too, right? Figuring out how to make it work, and then feeling good that you get to the point of, yes, this actually works, and everyone can then take note from it.
Absolutely.
So let's move on. Oh, this one says iPhone. So I don't know if does anyone have iPhone under Zoom? And they asked the question at 12:09 p.m. or I can just read it. What is your take on positioning the window when externally insulating?
It depends a little bit on what so let's say if it's a CMU, a concrete building with continuous insulation, you really want to move that window to the outboard side. So you really want the window to be installed in line with the insulation. So again, to kind of go back to one of the early examples I showed there, where was it? Maybe this one, right? So this example. In this case, you don't want the window in the middle of the wall, quote unquote, because that would put it back in the CMU layer, right? You really want the window installed in plane with the insulation. So wherever the insulation is, you want to try and, as a typical rule, you want to try and get the window installed in that layer. Again, it's more complicated because you do have to consider shading and some of the other bits and things. But for the most part, you would want to get that window back in line with the insulation.
Yeah, I can't see the image. I think you're not sharing your
Oh,
screen.
shoot, I'm
If
sorry.
you were showing
Oh,
something. Yeah,
I was sharing. I'm so sorry. Did you know what? I thank you, Jose.
there you go.
I think I
Yeah.
stopped sharing it. So sorry, I was trying to show this detail there. Maybe, yeah, that probably makes more sense now.
Yeah. So it's aligning the window with the insulation.
Right. So you wouldn't want to
Yeah.
put it in the middle of the wall. That's often the recommendation, is put the window in the middle of the wall. If you did that here, that would put it back in the CMU layer, right? That's actually the center of the quote unquote wall. Here you want to put, what you really want to do is put it in the center of the insulation layer. That's what you would typically want to shoot for.
Yeah. And I guess that's a good point also to kind of bring in the general conversation that, if there's no ability to calculate these thermal bridges and you're only having to identify them, understanding those basic rules is the best, and that's the best approach in general. Even if you're going to have some thermal bridge, at least you're mitigating as much as possible within the abilities of the team, and just the knowledge on using these softwares are complicated. I'm starting to do it myself, and it's an ordeal, but it's necessary. But if you don't get to that, following the basic rules of trying to stay in line the installation, reducing corners, changes in thicknesses, and that kind of stuff, it's the best way to go. So next we have another iPhone, and this one could be a longer conversation. So Ed, I wonder if you could try to just answer it as best you can. Can you explain isotherm lines? What are we looking for? Closely positioned together or wide gaps? What are they indicating?
Let me find it. Isotherm lines,
it's a loaded
right?
Question,
good question. No, it's a great question. Let me see if I find a good example. So maybe if you can see here, isothermal lines are lines of constant temperature. All those squiggly lines that you see in the drawing here are known as isothermal lines. They represent the temperature gradient, and they can often be analogized to a topographic map. So if anybody here is a hiker or is familiar with topographic maps, you know that where you see evenly spaced lines on a topographic map, that indicates a nice gentle slope. Whereas if you see the lines all bunched up together, that indicates a very steep gradient. A cliff, if you will. And that's the same thing that we see here. What we want is, when we execute these simulations, to see nice, evenly spaced isothermal lines. That visually indicates a lack of thermal bridge. When the lines get all squiggly, that's a technical term, when the lines get all squiggly and we see them all bunched up, that's a visual indication of a significant thermal bridge. So great question, but hopefully that makes sense.
So separation of them is not really an indication of how bad it is. It's how close they get in specific points. Not that they are, if they're all parallel to each other at very close intervals, it's still better than having them meeting at a point and then breaking apart, right?
Right. You can see in the detail here, you can see the window panel up above. They're pretty tightly packed, but they're nice and evenly spaced, meaning that there's not a lot of thermal bridging through the window panel at the upper part of these details. Whereas in the middle, you can notice that they get all zigzaggy and squiggly, and that is an indication of a thermal bridge, where they get all wacky in the middle there. So it's when they get all tortured and twisted that's a visual indication of a thermal bridge.
Got it. Up next is M. Reynolds. If M. Reynolds is not on the call, I can read the question. Thank you for a very clear presentation. Any suggestions as to how to hang siding on external insulation without reinstating thermal bridges? I guess without incurring in thermal bridges, probably.
Well, it's a great question. There's really only a couple ways to do siding over continuous insulation. You would either use metal fasteners, so you'd use a wood batten or a metal batten, and then you would fasten through the continuous insulation into the stud below. That's going to be some sort of a thermal bridge. RDH has some great research work on this, on quantifying the magnitude of the thermal bridges, as well as the sizing of those types of screws for that type of application. So I recommend take a look at RDH's research work on the subject. The other method would be to use some sort of a clip. And the best clips are fiberglass clips. Those are very low conductivity and have almost no thermal bridge. So using like a green girt clip or a Cascadia clip, one of those fiberglass clips, that would be a really effective way of getting a siding connection there with very low thermal bridging.
Yeah, thanks, Ed.
But check out the RDH stuff. It's useful.
Oh, sorry. Yeah. I'm unable to unmute myself.
What? Oh, great.
You said green something clips. And
oh, yeah. Sorry. So that's a brand name. Yeah. Green Girt. Is that with a U or an I? I don't remember. Green Girt, all one word. Somebody might have a link for that, maybe. Yeah, but that's a specific brand. GI. Okay, thank you.
Yeah. Green Girts.
I just proved I don't know how to spell girt. So green girt is one, and then Cascadia. So Cascadia is a manufacturer of windows, fiberglass windows, but they also make fiberglass facade clips.
Okay, that's great. Thank you very much.
Surely.
Yeah, let's see if we can get two more questions from Dennis Cecilmis from Datner Architects.
Yep. Hi.
Okay, go ahead.
I'm wondering if Ed can go back to the slide where he had 3 windows located in a different plane in the facade, the iterate slide. And if you could just kind of describe what's going on there, because I think it's like you're explaining in the response to the questions. You have, both interior and exterior insulation, and you're moving the plane of the window. Could you talk more about the effects of that on condensation in general?
You're muted, and share your screen too, so we can see the slide.
Yes, absolutely.
Thank you.
Okay. Yes, great question. So what you're seeing there are 3 identical window details. Well, not identical, but three details of a window and a stud wall with continuous exterior insulation. So the interior is on the left, the exterior is on the right. And what you're seeing there is just the difference in the psi value depending on where you install the window. So remember, I said you want to try wherever possible to get the window in line with your primary insulation layer. In a case like this, where you have a steel stud wall with continuous exterior insulation, the primary insulation layer is actually that continuous exterior insulation. And so moving the window so that it's in plane with that layer actually yields the best psi value. You can see here that the psi value for that case on the far right is 0.022. That's 50% of the middle case at 0.051, right? So we're getting a much better psi value in that far right case there. And as a result, we're going to have less heat flow and better interior surface temperatures. Now, we didn't show surface temperatures and the temperature factor in this particular case, but as a general rule, as you reduce your psi value, you'll end up with better interior side surface temperatures. Not always, but as a general rule, that is a pattern that you can expect. It is a little more complicated than that, but for the most part, that's what you can expect to see. And so what you're seeing here is basically more durable on the right, less durable on the left. Durability being a condensation risk, a likelihood of mold growth in these cases there.
Thanks, Ed. And I guess it is, we have 2 minutes. So let's go over to Patrick Fritsch. Patrick Fritsch's question. If Patrick's online, you can ask your question or I can read it.
Yeah, hi. So I'm just wondering, I'm a recent certified passive house designer, and I'm just wondering the thermal bridging, you have a recommendation as to, like, it's kind of confusing as to which one is used for what and which one do you start with to learn?
Which tool you mean to say? Is that the question?
Yeah.
Which simulation tool?
Yeah, especially I'm more geared to like single family, so it's kind of I'm just like, okay, Flexo, Therm is pretty cheap, for a residential.
It's a really good question. So we get that question a lot. So I'll try and answer it in a way that's not super rude. If a roofer came to your job site, you hired a roofer to work on your house and he showed up at your job site and he had a ladder that was missing 3 rungs and was broken on one side and was held together with duct tape and started to climb it. And you said, hey, what's with that ladder? And he said, well, I got it for free out of the dump yesterday. You would say, get the hell off my job site. And that is my opinion about free tools.
Okay,
invest in Flixo.
That's super helpful, because I mean, we have the same philosophy with our design tools, right?
Yes, exactly. You should use Flixo. So for the tool, the projects that you're working on for that scale, I would strongly recommend Flixo as the ideal tool for that. That is, in my opinion, that's the best tool for the job when it comes to 2-dimensional thermal bridge analysis. It's very, very intuitive. It's very reliable. It's very professional. It's very good at making output reports, and it's a great all-around tool. And so I would strongly recommend that one for typical projects.
And so just to tag on here, would you, as a designer, would you recommend that I even bother, or just get somebody like you that's doing it? Is it worth the time?
No, I mean, I think my basic opinion is that all of this work should be done by the architects. This is the best person to do this work is the architect, because they're the ones detailing the building. And this work really should be done alongside and in parallel with the detailing phase. Is it realistic? I don't know. That's a bigger discussion. In practice, in practice, we see a lot of outsourcing and specialization, but in an ideal world, this type of work would be done, at least at an initial level, by the architecture team. I think, this type of iterative development, this is best done by the architecture team themselves, rather than trying to outsource it.
Yeah, which is why we get certified as a passive house designer, right?
Yeah. And once you invest, if you invest in a good tool like Flixo, you'll find that this type of iterative work is really quite straightforward and quite fast. Much easier than using some other free tools that shall not be mentioned.
That's very helpful. I was going down the rabbit hole.
Sure.
All right, thanks, Ed. Thank you, Patrick, for that good question. And I guess that's the main point. Some people will want to figure out once they learn about this and then they get into the rabbit hole of designing it. Like, how can I get the numbers? Then you're, oh, okay, these are the options. Which one should I pick? I gotta say, I started with the ladder, and yeah, I fell off of it a couple of times. It's not a great tool to have, and then you end up going to Home Depot and getting the proper stuff. So yeah, we're at the top of the hour. I think what we're gonna do, I think it would be nice to do for these types of conversations, that we'll gather the questions. And Ed, if you don't mind, can I send you the remaining questions and just add a couple notes, and then we can put them on the YouTube description of the video, so that it's there for anyone that comes in and they may get some answers from them, aside from the ones we have on the recording. So yeah, with that, I guess everyone, thank you for joining, and we'll see you on the next one and on next week's event.
Absolutely. And thanks everybody. Thanks to you, Jose, Zach, Kim, Michael, everybody at Passive House Accelerator. Thanks for you guys for putting these on. Always great and good to see everybody.
Thank you, Ed. That was amazing.
All right.
Thanks, everyone.